So welcome to the video lecture series on principles of compiler design. In today's video lecture, we'll be learning about the most prominent topic called the phases of compiler. So phases of compiler means in how many stages the compiler is getting developed. In what are the stages we pass through to develop a compiler. And this is Dr. K N Sivabalan. And to start about what is meant by a compiler. So a compiler is a software. It's also a program where it acts like a translator. So what is meant by a compiler? A compiler is a translator which converts program written in high level language to machine level language. So now we write a program in English form that is not actually understandable by a computer system. So to make the computer to understand, we have to convert the languages which is written in English form to a machine level language, which is actually closely recognized by the computer system. So if you do that, then that role is actually done by compiler. So compiler role is to convert from high level language to machine level language. So that is the role of the compiler. Now here I have given a visual representation of how actually a compiler converts a high level program to a low level program. This is a simple depiction of a compiler. So when we talk about compiler, we can have a high level language called as C equal to A plus B. Now this C equal to A plus B is a high level language which is not actually understandable by a computer system. So what happens is this compiler actually converts the C equal to A plus B into a language where system can easily recognize and understand and execute. So what happens here is the C is equal to A plus B is converted as add A comma B, MOV B comma C. So this is actually written in assembly language. So high level language is actually converted to a assembly level language. That is also considered as a low level language. Now these are called as the phases of the compiler. We have 6 phases of the compiler, and apart from 2 supporting phases called as symbol table and error handling. The first phase of the compiler is called as lexical analysis, followed by syntax analysis, then semantic analysis, and intermediate code generation, code optimization, and code generation. So this we will be stepping inside each and every phase in a detailed manner. Now we start about what is meant by lexical analysis. So this phase actually is called as the first phase of the compiler, which reads the source program from left to right and converts that into lexemes. So lexemes is actually called as some elements where we can have a variable, we can have a constant, we can have an operator. All these are actually called as lexemes. Now, normally this first phase, lexical analysis, takes the source program as an input. Now, finally, what happens is this lexemes are actually represented in the form of tokens. For example, when we talk about A is considered as an identifier or variable. Now, when we talk about this equal to is called as an operator, and this 5 is called as a constant. Okay. So, we actually give some meaningful names to these lexemes, and that is called as tokens. And another important feature of this lexical analysis, it actually removes all the white spaces in the program. So unwanted spaces will be removed in this lexical analysis. Now, what this lexical analysis does, okay, it converts this each and every lexemes into a respective tokens. Now we have a graphical representation of this simulation kind of thing. It reads the character one by one from left to right and converts each lexeme as a tokens. For example, now you have a pointer which is standing in this high level statement called as profit. Profit equal to cash plus product sold into 10. This is called as high level statement, and this pointer is standing in profit. Now this profit is actually called as a variable. Okay. Now we have to classify this variable as an identifier, isn't it? So now what happens is this profit is actually given to a lexeme, and then the corresponding token is called as an identifier. Now this identifier is actually depicted as identifier 1. Now we move to the right side. When we move to the right side, you can see equal to is called as an operator. Okay. Now equal to will be given as a lexeme. The corresponding token to that is called as operator. Now again, we move to the right, one step to the right. Now you can see that cash is called as an identifier or variable. Now this cash is called as a lexeme and the corresponding token to that is called as identifier. Since this is the second identifier, we have named it as identifier 2. Now when we move on the right, we can see a plus. Plus is called as an operator, isn't it? So now plus is considered as a lexeme. The corresponding token to that is called as operator. Now when we still move on the right, you have product sold. Okay. Now when product sold is called as a identifier, now product sold will be moved to lexeme and then the corresponding to that is identifier. Since this is called as a third identifier, we have named it as ID3. Now we move on the right, again you see an operator called as star. Star is called as an operator, that is called as a lexeme, and the corresponding to that is token is called as operator. Now the last one, when we move on to the right, the last one we can see 10. 10 is a constant, isn't it? So 10 is actually moved as a lexeme and the corresponding token to that is called as constant. So this is how actually a lexical analysis functions, converts each lexeme to their respective tokens, reading from left to right. Now the next is a whole depiction, a comprehensive way of depicting what a lexical analysis does. So far we have learned about in an elaborate fashion how it is getting converting to a respective token. But in this case, we have given a high level statement, and finally the final outcome of this lexical analysis will be a complete tokenized statement here. Now this statement, product equal to profit equal to cash plus product sold into 10, will be converted as ID1 equal to ID2 plus ID3 star 10. So we have already learned about how this identifiers has been named in the previous slide. Now when we talk about syntax analysis, this phase is also called as parsing phase. This takes the tokens generated by lexical analysis and verifies whether it is actually conforming to the grammatical rules of the language. And the grammar which is given for this syntax analysis is called as context-free grammar. Once the token actually adheres to the grammar, then the respective abstract syntax tree is getting generated. If not, then error will be given to an error handler, and then error handler will take care of that with appropriate notifications. So this is how actually a syntax analysis functions. Now, what is meant by abstract syntax tree? We have, when we construct abstract syntax tree, there are certain rules to follow. The operator will be always represented as an internal node. So any kind of operator will be represented as an internal node, and an operand will be always represented as a leaf node. So this is the set of rules or bunch of rules which is used to construct abstract syntax tree. Now, when we try to construct abstract syntax tree, normally the precedence has to be followed. Here, star has a higher precedence compared to plus and equal to. So now we will start to construct from the precedence order. So since star is having the higher precedence, we actually move the pointer to star here. Now star is called as an operator, so it is actually named as an internal node here, represented as an internal node. Now we move on the right, you can see that 10 is called as a constant. So 10 is called as a constant, and since it is constant, we make it as a leaf node now. We make that as a leaf node. Now when we move on the left side, you can see that there is ID3, because star is actually operating on two operands. One is ID3 and another is called as 10. So ID3 is called as an operand, so it has to be represented as a leaf node on the left side of star. Now again, when we move on the left, you can see that plus is an operator. So operator should be definitely an internal node. So I make plus as an internal node here. Now when we move again to the left, you can see that ID2 is called as an operand. So ID2 operand has to be represented as a leaf node. Now see here, ID2 is represented as a leaf node. So it is actually pasted on the left side of plus. Now when we again move to the left side, you can see equal to is called as an operator. So it has to be represented as an internal node. So equal to is called as an operator, it is represented as an internal node. Now when we move on to left side, you can see ID1. So that final results has to be stored in ID1. Now ID1 is actually on the left side of the equal to. So ID1 is an operand, it is represented on the left side. So this is the way of constructing an abstract syntax tree. Now what is meant by semantic analysis? So semantic analysis actually verifies the input in the symbol table, and it also performs the type checking. If it adheres to the rules of the language, then the respective semantic tree or annotated parse tree will be created. This also keeps track of the identifiers and its types and expressions connected with that. Now, this actually always checks the undeclared variables and performs typecasting, and if there is any improper arguments represented in the program, and it will report it as semantic error. So semantic analysis actually adds meaning to the expression. That is called a semantic analysis. Now when we talk about the previous statement which we have done in syntax analysis, I am taking the same statement here. Now let us assume that ID1, ID2 and ID3 are float operators, or float operators are otherwise called as real operators. So any value which has a decimal point notation, that is called as a real operator or float operator. Now when we talk about 10, 10 is actually called as an integer operand. Okay, indeed 10 is called as an integer operand, whereas ID1, ID2 and ID3 are called as float. Now what you have to do is, since rest of the operands are actually float, 10 should also be converted to float. Okay, so now when we try to convert that, now 10 is actually should be converted into integer to float, and you can see here that now we represent that 10 has to be converted from integer to float, and it is making a move here. Okay, now this is called a semantic analysis. You can see that integer to float actually converts 10 to 10.0. Now what is meant by intermediate code? The intermediate code is a code which is actually placed between a high level and machine level language. So we can say a mediator level of code here. Okay. Now it is also called as a three address code. There are many forms of three address code here. We talk about postfix notation and quadruples, triples, indirect triples. All these are called as three address code. Now the code maintains a precedence order of the source program. Now you cannot generate the three address code as it is directly in a sequential order, because once you try to generate intermediate code, then it should actually carefully follow the precedence of operators which are used in the language. For instance, when you have in the same expression, when you have plus and star, normally we have to evaluate star first and then plus. Okay, so we have to write the intermediate code for star first, and then we have to, it should be followed by plus operator. So that's how actually it goes. Now it generates a semantic representation of a source program. So this is about the intermediate code generation. Now we will take this semantic tree, and then we will try to convert that into an intermediate code. Now we have to evaluate the tree from bottom to top. Okay, bottom to top fashion we have to evaluate. When you talk about bottom, so first thing, integer to float has to be performed on 10. 10 is an integer, so that has to be converted to float. So now we can take that portion and try to convert that. So now what happens is, this into to float is applied on 10, and then T1 will be having the value called as 10.0. Now when we move on the top, we have star here. It should be performed with the converted value of 10 and ID3. So now we take this form, and then we write an intermediate code called as, first intermediate code is called as T1. Now we write T2, whereas ID3 is actually multiplied with the converted value of 10 that is already stored in T1. So we are writing it as T2 equal to ID3 star T1. Now we go to the next step forward on the top. We go to plus now. When you see plus here, Plus is actually converted, added with ID2 and the rest of the value of star here. So star is represented with IT2. Now ID2 plus T2, we gave the value we got the value called as T3. Now finally, we move on the top, we have equal to, and we have ID1 should be the rest, entire result has to be assigned to ID1 here. So now when we take this, now the entire result is actually stored in T3. Now it will be stored as ID1 equal to T3. So this is called as an intermediate code generation. Now when we go to the next step called as code optimization is actually removal of unwanted instructions and unwanted memory should be removed. Okay, so in order to improve the efficiency of the code, we actually perform this operation. So when we remove memories and unwanted lines, the code will become efficient and faster. So that is the reason why we are doing this. So now see here, when we take out this code first, we can see that T1 is equal to into float 10. Now what happens here is 10 will be converted to 10.0, that's all. Okay, so when we take this code first, 10 will be converted to 10.0. So this is an unwanted code. So instead of taking this 10 into 10.0, directly you can write it as 10.0. So now, now you take this next step. Now this 10.0 is actually multiplied with ID3 because it is stored in T1. Now T2, that final result is getting stored in T2. So instead of doing that, we can directly write it as T2 is equal to ID3 star 10.0. So that's what it is written. So two instructions has been reduced to one instruction. Now when we move to the next equation or next code, you can see that T3 is equal to ID2 plus T2, and this T3 is actually finally stored in ID1. So unwantedly I am taking a value called as T3. I take that value and then I store it in ID1. So instead of taking this ID3 T3 value, I can directly put ID1 is equal to ID2 plus T2. So now see here, that's what has been written. So unwanted space is T3 is having unwanted space here. So two times I take the copy, the value and transfer to ID1. So directly I can just put the result of ID2 plus T2 in ID1. So that's what has been done here. So this is called as code optimization. And the final phase is called as code generation. So what is code generation? We take the optimized code as an input. Now this intermediate code, optimized code will be converted to a machine code or low level language which is specific to a computer processor. So it allocates memory to the program. On other terms, it allocates memory to the data in the form of registers and then it gets executed. Now we will take the example here. Now I take the previous example, T2 equal to ID3 star 10.0. Now you take the first instruction, first we will take 10.0. So when you take this 10.0, first we have to move this to a specific register. Register is nothing but a small memory locations which is available inside a processor. Now I just use MVI, move immediate. So I move this 10.0 to a register called as A. Now when we take the first instruction, there is another operand called as ID3. Now this ID3 has to be moved to another register. Okay. So now I just move MOV B comma ID3. Now A is having 10.0 and B is having ID3. Now what we have to do with this instruction? ID3 should be multiplied with 10.0 and that result has to be stored. Isn't it? Now A and B has to be multiplied. This entire result. So I should not write here as add B, it should be multiplied here. Okay, so I just make it here. Multiply MUL A comma B. Okay. Now when we go to the next one, we take up ID2. ID2 is a separate operand. So I move this to C register. Now, the first result, that is multiplication of A comma B, will be the final result will be available in A here. Okay. Now, the next is this ID2 should be added with T2. So, now what I am going to do here is I take this entire instruction, I make add A comma C, because C have ID2 and A have the result of the previous instruction, isn't it? So, now finally what we are going to do here is we actually make this ID1 is equal to ID2 plus T2. So, now the final result will be available in A now, that has to be moved to ID1. So, I am just making it as MOV ID1 comma A. So, that is about the code generation. Now, you can see here that you have 2 high level code instructions that has been converted to 6 low level instructions. So, this is called as code generation. Now, the final thing is actually a symbol table. So, we are supposed to go, we are coming to the end of the phase of compiler here. Symbol table is called as a data structure which maintains the variables, its addresses, its data types, and also the function names, the constants, everything it actually maintains. Now, this is one of the phase which has interactions with all the phases of the compiler, spanning from lexical analysis to the code generation phase. And it also connects with error handler. Now, see here, I take the previous high level instruction profit equal to cash plus product sold star 10. Now, pointer is actually standing on profit. We read from left to right. Now, what happens is profit is called as a symbol and its attribute is identifier 1 and its data type is actually float. And a memory location is actually assigned to that. Let us assume that it is having a memory location called as 1000. Now, when we move on the right, we can see cash. Cash is another symbol or variable. Now, it is named as identifier 2 and its type is actually float data type. And it has a memory location called as 1500. When we move on the right, still we have another variable called as product sold. Now, this is going to be identifier 3 for data type and it has a memory location called as 2000. Now, when we move on the right, now this is not called as a memory location, this is not called as a variable, but it's called as a constant. And this constant is actually of integer type and it is actually stored in a memory location called as 3000 for assumption. Now, finally, we will have the error handler. So, error handling is actually responsible for notifying the user or a developer whenever error is made while operating in the code. So, lexical analysis means when you actually spell a token in the wrong way, misspell a token in the wrong way, then it is actually called as lexical analysis. Syntax analysis means, for example, if you are missing the parenthesis in a if loop or for, then it is called as syntax error. An intermediate code error means if you have any mismatched operands for an operator. For example, when I want to add A and B, where A is called as an integer and B is called as a string, then obviously you cannot add A with B. So, such kind of error is called as intermediate code error. Now, the next is called as code optimization error when the statement is not reachable. Say, for example, when I have I equal to 2 and if I had a set of statements only when I is equal to 1, well, then it will get executed, means then such kind of problem is called as code optimization problem, because that statement will never be reached because I has been already set to 2 and it is never going to become 1. So, that code, the code where when I is equal to 1 has to be executed, will never get executed. Now, the final level is called as code generation error. When the memory is full, obviously the system is actually packed with troubles here. So, in that case, you cannot allocate any registers for executing the code. So, then that is called as code generation error. And finally, when symbol table error means when you have multiple error for multiple declared identifiers. Same way identifier is declared, that obviously result in a symbol table error. So that's about phases of the compiler, and thanks for watching the video. Have a good day.